thank you for showing up this late into the conference and right after lunch. I hope you're not too tired. And before we actually start, making weird noises, I would actually like to do a little bit of show of hands. Who of you heard of Eclipse SUMO before? Oh yeah, me too, quite a bit. And who of you have also heard about Eclipse MOSAIC? Okay, yeah, that's what I guess, quite a few less. And last question, who of you heard the words digital and twin next to each other? Okay, but I think a lot of you are from the SDV community. We do a kind of different kind of digital twin. And yeah, let's start off with an introduction now. My name is Moritz Schweppenhäuser. I'm a researcher at Fraunhofer-Gesellschaft in the Department of Smart Mobility, working in the team of simulation and validation. Also, when I say researcher, I'm really a software developer at heart. And today I'm very glad that I can be joined by Robert, who will introduce himself.
Thank you very much. My name is Robert Hilbrich. I'm just the small and minor sidekick of this show. I'm working at the German Aerospace Center in Berlin, and I'm one of the two project leads of the Eclipse SUMO project.
Yes, thank you. And yeah, I think we hold the record for the longest title in this EclipseCon. So we are going to show you how you can use the tools Eclipse SUMO and Eclipse MOSAIC to unleash the power of digital twins for efficient urban mobility management in the city of Berlin. And on the topic of Berlin, I put this picture here to really emphasize that there is a lot of different kinds of mobility going on in our cities. So in the back, you have your normal vehicles, you have buses, but also you can see the tram in the middle, you can see people walking around, and also some people using their bike. There's a rickshaw. Fun fact, this picture is actually quite old because there are no e-scooters at all. And yeah, what I want to emphasize with this picture is that I think we don't have to start a discussion with climate change going on and also growing cities, more populated cities, that there's really a change in how we need to consume mobility. So in German, that's Verkehrswende. And this is really what we are focusing on in this talk. And yeah, on the topic of questions, to put these, like this huge need for mobility into numbers, I actually have another question for you. So yeah, just yell the answer at me. How many individual motorized trips do you think exist for one day in the city of Berlin? Individual motorized trips, meaning people using their private cars going to work or whatever, and one day means 24 hours. So yeah, just anyone, just yell any number at me.
Maybe we should do this as a kind of auction. Who thinks it's more than 100? More than 1,000? Do you want to continue?
Yeah, more than 10,000? More than 100,000? More than 1 million? More than 2 million? More than 3 million?
But you're not getting any prize, all right?
No. I mean, you have some sumo stickers. Okay, and then more than 5 million, anyone? Okay, more than 10 million? Okay, that's where it stops. So yeah, I was actually a little bit mean to you. There are a magnitude of factors that actually influence that number. Yeah, first of all, of course, the population size, so the amount of residents just influences this number, yeah, just linearly. Then one thing we saw during COVID, that the way how we design our life, our lifestyle, has a huge impact on this as well. If nobody is going out because we all work from home, people will use their cars less. And the last thing I would like to point at is the percentage of motorized use. So really, if people move away from their cars, using public transport, using e-scooters, or using any kind of new future mobility that no one has thought of yet, this number is also affected. And taking all these factors you see here into account, we came up to an estimate about around 2.25 million trips. So I think the broad agreement was quite right here. And all right, this is a really large number. And this is where digital twins come into play. And first of all, we all have different perspectives on digital twins and come from different domains. I would like to first say that this is not a Black Mirror episode, so anyone who was expecting putting brains into computers is wrong here. And secondly, I learned in school that definitions are good, so I took this one from Wikipedia, which says digital twin is a digital model of a real-world physical system that serves as a digital counterpart of it for practical purposes such as simulation, integration, and testing. And I marked some words here, and because I'm more of a visual learner, I put some pictures here as well. So for us, as coming from the traffic research domain, the real world really only consists of these factors. So first of all, we have the road network, including also traffic signs, thereby implicitly including speed limits, but also traffic lights, the amount of lanes on a street, and so on. Then what we can do in the real world is measure actually traffic. So you can do that by using traffic cameras or just standing at the side of the road and counting how many cars are coming. And these two blocks of information are fairly static. So the road network maybe changes once in a while because there's a new street built. Traffic densities are really averaged over the entirety of days, really similar. So the traffic really looks similar on a Monday compared to Tuesday. Weekends are of course different, holidays are different, but the average is fairly similar. So this is also more or less a static number, and then we have dynamic information, which includes traffic light schedules, which can change when more cars are traversing a junction. There are construction sites, which can, of course, pop up in a second and be removed in the other. And then I put traffic monitoring here. What I mean by that is some form of estimating the current density, so really what is going on in the street right now. So this is the real-world physical part. And next to it, I put the digital twin. What we understand as a digital twin is that we first need a representation of the road network, which is a map, or can even be a high-definition map, which includes all these factors I mentioned before, so all the roads, but also traffic lights, traffic signs, the amount of lanes, and all that information. Secondly, what we can do with traffic counts is generate demand, or what we call demand. So when are vehicles driving where, and what routes do they take? And what I put here as well, because it becomes important for the later part of the talk, is that we can also simulate sensors, which we could also have in the real world, but we're really able to also do new kind of sensors, or sensors that would be really expensive to deploy on a large scale in the real world. So for example, equipping 2 million vehicles with GPS sensors and getting all that data is really expensive. And last thing on the slide is that you can design digital twins in a real-time manner, and you can actually get live data from the real world, put them into the digital twin, and see what happens. And the other way around, if you do some research on your digital twin, you can use that information in the real world. So that brings me to my next slide. Why should you or we care about digital twins? And there are two main factors. It's first, that was a spoiler, to understand complex systems, and secondly, to improve existing solutions. All on the manner of understanding complex systems. I put a really simple example here for everyone to understand. So what happens if we put a construction site here? How is the traffic affected on this road, or really any other kind of road in the entirety of the road network, which is a really powerful tool for traffic planners, and they can just put this into the digital twin and see what happens at the other kind of roads. And the second thing I put here, which is relevant for the rest of the talk, is a use case actually. Can we improve existing traffic state estimation solutions like those of Google or TomTom? You probably all use this when you commute to work by car. You see your green, red, yellow edges. Green means I can go fast, red means I need to go really slow. And can we use this solution and improve it by using also information from perception sensors? So this is actually part of ongoing research that we at Fraunhofer Focus are doing right now. So how these systems typically work is that you have vehicles. They periodically transmit data to a server in the cloud, which contains spatiotemporal information. So where are you, how fast are you going, and at what time step are you going, are you there? And then the idea that we had is, why don't we use data from cameras? We each have mobile phones. We can put them behind our dashboard and get additional information. And this is the research thesis we had. We are not really about improving traffic state estimation, but more about how can we reduce the number of vehicles that we need. Because as you know, a lot of you are using Google Maps probably, and they have millions of users. And is there a way that we can achieve the same level of traffic state estimation with fewer vehicles? For example, there were talks about fleet management, using a few vehicles of a fleet that gives you data, which you can then later potentially even sell to other services. And now that you heard about digital twins and some use cases for it, we would like to go into the tools that we are using for that. And therefore, I would like to hand over to Robert.
Oh, yeah, this is the beginning of the small sideshow here. SUMO, I guess most of you, as we've seen at the beginning, most of you have heard about SUMO before. So there's not much new for me to tell you now. SUMO is a tool that we've been developing at the DLR in Berlin for more than 20 years now. You can build digital twins of cities easily to see or to simulate how all the vehicles in this city move. It is not only limited to vehicles, you can also put in pedestrians, trains, ships, basically everything that moves in your city. You can even simulate public transport, so people can actually get into a bus, leave a bus when they reach their destination, to have a real multimodal simulator. Yeah, and SUMO is open source. You can readily use it, and it's not just a player where you can hit play to run your simulation. It also comes with a variety of tools to actually help you build such a simulation. And how does it look like? I guess most of you have seen a similar SUMO simulation. This is from an urban scenario where you basically have a bird's eye view on top of the road network, and you can see all the vehicles moving as we are slowly zooming in. You can influence this simulation while it is running. You can add cars, you can close down lanes, so you can really, really use it as a very versatile playground for your research, for your project, for practical applications actually. So you can really see what's going on there and look at your city from a new perspective. All right. That is a SUMO, as you'll love it, hopefully.
Yeah, and this is a good transition, actually. We are actually SUMO users coming from Eclipse MOSAIC. And what Eclipse MOSAIC is on a really big picture is a way to couple simulators from different domains I have to mention time-discrete simulators, in a way that they can interact with each other, and you can get a result which gives you the big picture. And how we achieve that is, at the heart of it, really the runtime infrastructure, which is based on the high-level architecture, if you want to read up on that. And that runtime infrastructure really takes care of of the federation management, time management, and interaction management. And what MOSAIC also offers is not only the runtime infrastructure at the heart, but also couplings for a couple of simulators and even some bundled simulators. So we have here at the top right, of course, SUMO, but we are also able to couple other simulators, also vehicle simulators, so where you would more in detail simulate the movement of the wheels and stuff. So yeah, we are actually able to couple color. This is not quite open source yet, but on the way there. Then where we actually are coming from is the simulation of V2X communication. Probably a lot of you heard about it. So we had the need of coupling the movement of vehicles with some form of communication. So, and that's what we did. So we coupled the NS3 and the Omnet++, which might ring a bell for some of you. But also, MOSAIC comes coupled with two really efficient and simple to use network simulators. The simple network simulators for ad hoc, so Wi-Fi based communication, and then the cell simulator, which aims to simulate cellular communication. And then the thing that really brings it together from the user's perspective is the application simulator, which enables you to really map any kind of application that you can write yourself. It's Java code, and offers an API for you to do that, to put these applications and put them on different units, different players in your digital twin, in your simulation. So you can create roadside units that can communicate with your cars. You can create servers that are in the cloud, but you can put, of course, also applications on vehicles. And then once you have your running scenario, probably a SUMO scenario, you have your communication set up, you have an application that you want to test, which is the new traffic state estimation, for example. You bundle that all together, and then you can, what I showed you before, do actually these kinds of tests, and can also see what is really important. How many vehicles would we have to use with perception capabilities to get this kind of traffic state estimation? And to look at how many we use, MOSAIC also comes with a lot of evaluation tools. So yeah, there you can write during simulation, you can write some files, you can also aggregate this data that is written to some statistics. And of course, there are visualization tools, which I think is really important in our domain. And lastly, it's also what I put down here. You can really easily couple your own simulators. And this isn't restricted to traffic or communication. I think we had a request once from someone who wanted to simulate the building of an oil pipeline, and they actually considered using MOSAIC. So this is really a powerful tool, and I hope some of you will at least Google it. And now that you know about the tools, I was actually a little bit unfair in the beginning. I just asked the question, showed you some factors, and then gave you a number. So how did we actually come up with that number? And it's actually simple. We just simulated it. And we came up with a digital twin for the city of Berlin, which, yeah, you can see a short cutout here. This is in the morning hours. I think the Alexanderplatz is around here. And okay, now you know that there is a digital twin, but how can you trust the number I gave you at the beginning? Well, we had that scenario and we validated it, and we did that by comparing it to real-world traffic counts. And you can see that more or less we really hit the mark quite properly in the end for most of the streets. You can see down here that there's some traffic demand missing, and there's, of course, some other edge cases in the big scenario where we aren't quite up to reality. And yeah, the best part about that is that it's actually open source. You can find it here. We called it the Berlin SUMO traffic scenario, so the best scenario. It consists about 800 square kilometers of area in a 24-hour time frame, with the number I showed you in the beginning, around 2.25 million individual trips. And if you're more interested in how we generated that data or that digital twin and what assumptions we made and how we validated further, we wrote a paper about it, which I think should be openly accessible, and you can read up on it. And yeah, with that, we're almost at the end. I will give over to Robert to have a little shameless plug.
Thanks a lot. So I hope everyone saw that we were able to simulate almost 30,000 vehicles here. How long did the simulation actually take?
I was hoping for a question from the
All right.
crowd, but running on a fairly modern PC and using only the SUMO simulation without any MOSAIC on top, it ran for about 4 to 6 hours, depending on your CPU.
So we're talking more than a real-time performance here. So perfect. Thanks a lot. This is just the beginning of the discussion and the road that lies ahead of us. MOSAIC and SUMO are just two of the main building blocks in the open source world that we would like to develop further in order to build digital twins of cities. There are more projects coming. I hope you saw the talk from Martin from 7 Principles yesterday. There's more in the pipeline, in the tools section for these kinds of topics. We would like to continue the discussion about the development of these tools in one of the newly founded interest groups, the Open Mobility Interest Group. You can find out more about it at openmobility.eclipse.org. And if you are already an Eclipse member, it's really just a matter of clicking one of the forms to actually join. There's no signature necessary. And we would very much like you to join this interest group, talk to us about your requirements, talk to us about your needs. Maybe you can even contribute with data or with code. All this discussion I would like to very much to continue in the new interest group. There's also the links for SUMO and MOSAIC down there, also to the best scenario, which is in fact the best scenario with, I think, the highest number of cars that we have in one of the open source scenarios. So once again, thank you very much for listening. It was a pleasure, and we're open for questions.
Yes, thank you from my side too.
Are there any questions? We got the mic there, if you...
You can also sing a little bit.
Did you guys try out the best scenario while we were talking? No one did? Okay.
All right, perfect.
Thanks a lot.
Woo, give it up. Yes, thank you.